All right. Okay, so what we were talking about was mainly how to make electromagnetic waves. And basically, like, we watched this video, but the key point is that in order to make electromagnetic waves, you need accelerating charges. So in this case, what we're seeing a picture here of are like a plus and a minus charge, and they're interchanging positions like this, oscillating. And in fact, you just need the one charge, but then it's sort of a bit more symmetrical to have both charges. And if you have these accelerating charges, then this produces electromagnetic waves. And I mean, this video sort of explained why. It's basically because, if you just have a static charge, then the electric field lines just go or in all directions. But then if you move it, like if you accelerate it, then you develop these sort of kinks in the electromagnetic or electric fields firstly, and then those kinks kind of develop into waves which sort of propagate out. And the key to all this is actually the key concept is that basically a changing magnetic field produces an electric field, and then a changing magnetic field produces an electric field. And so if you have both of them changing and then both of them producing each other, then basically it becomes a self-sustaining process. And that's actually what light is, which is, quite a revelation, because, doesn't seem particularly so sort of related to electric and magnetic fields, but actually it was discovered in the late 1800s that these are basically the same. So yeah, so there's various different wavelengths, and ranging from visible light to X-rays to radio waves. And yeah, in an antenna, this is basically a device in order to either generate or receive such electromagnetic waves. And so it's essentially just a piece of long metal, and then the charges inside the metal just sort of bounce back and forth between the edges. And so at any given time, you'll have a plus and a minus charge, and then it will flip a half cycle later. You can also have a so-called monopole antenna using tricks with sort of metal surfaces, but maybe we won't talk about that. And this is basically how radios work. So radio is basically something that, well, firstly, the radio station has to send the signal of the radio frequencies out, right? So it needs an antenna to broadcast it. So this is the radio station, and basically it's just, charges going up and down this large antenna. And then you also have another antenna to receive it. And basically what you're trying to do here is trying to catch these electromagnetic waves. And it basically does the reverse process of moving the charges around. So in the first one, we were trying to generate electromagnetic waves or radio waves, if it's a radio, by moving the charges. And over here, we're trying to use the waves to move the charges, right? And then so we're converting it back into some kind of oscillating electrical current. And then using that oscillating current, we can get a signal. And that's basically, the signal that that you're listening to when you listen to a radio, old-fashioned radio. Okay, and the problem here is that it's very weak. So if you did this, like maybe your antenna would just have to be right next to the radio station. And of course, that's not very convenient. You want to, listen to your radio wherever you are. So you amplify the signal, and the way you do that is a bit like how it's done in a guitar. You have like an oscillator. And in this case, well, in the case of the guitar, the oscillations are actually the, air waves. So we're sort of oscillating air, that's sound. And basically we're trying to create a box such as to oscillate the sound waves as much as possible. In this case, we're not trying to do any kind of sound waves. What we're actually trying to do is trying to make a oscillator that's actually for the electrons inside this wire, or the antenna, and then the antenna is connected to a wire. So you need basically some kind of oscillating electrical circuit. And that's basically exactly what this tank circuit is, or I'm more familiar with the term LC circuit, which is L stands for the inductor, and then C stands for the capacitance. It's made of an inductor and a capacitor. And capacitor is nothing but it's like a little rechargeable battery. It stores a little bit of charge. And basically by applying a voltage on the between the terminals of the capacitor, it will charge up the capacitor. And basically capacitors are a little bit like the electric field version of an inductor. And we played a little bit around with what inductors do. But basically inductors like to maintain kind of current. So if it has some current, it will try to maintain that current. Capacitors like to store charge, and basically the energy is stored in the electric field in this case, and energy is stored in the magnetic field. And so what ends up happening in this LC circuit is that sort of energy is going back and forth between the inductor and the capacitor. And over here it's in magnetic field energy, and then over here it says electric field energy, and then it sort of shuffles back and forth just like a pendulum. And we had a go at making this kind of circuit. I think this is where we got up to, and well, I redid it so I can show you again. So I get it on the right page. So yeah, so we had something like this where the inductor and the capacitor working together to produce this oscillating current. So in this ideal kind of circuit here, this will just keep on oscillating forever. Okay, and right, so I think that's basically where we got up to. Yeah, okay, so just to explain what's happening in this circuit a little bit more, so maybe I'll just go back to this electrical circuit here. So for example, let's just remove this leg here, and if you close this switch here, what happens is that it charges up the capacitor. Okay, and once you charge up the capacitor, it's like a rechargeable battery. I can remove the battery, and it's still charged up here. Now, if I get a piece of wire here and then connect it, what should happen is that this will start to move. And basically, why it starts to move is that it didn't really charge it up very much. So hold on, let me make a yeah. I just cranked up the voltage here to 34 because it wasn't moving very much. So okay, so let me just try that again. All right, so now we can see it's sort of.
I think you're sharing the wrong screen.
Okay, I'm sharing the wrong screen. Okay, thank you. Okay, there we go. All right. So what I was doing there was I made this slightly bigger battery, so 34 volts here, and I made this a bigger capacitor. Okay. And all right, so let me just redo that because I think I wasn't sharing the right screen. So here I've charged up the capacitor. So now the capacitor is fully charged. There's no wire here. And now let's connect the wire. And then when I connect the wire, oh, sorry, I messed up. Okay, sorry. Again, all right, so I've charged up the capacitor. I've opened the circuit, and right, okay, so I connect the wire and then it starts to oscillate. And so let's just look at what's happening here. So at this moment here, the capacitor, it was fully charged. And the reason why it'll start to well, let me, I want to pause it at certain points in time. So at this point, it's the capacitor is just about fully charged. Now, this plate is full of positive charges, and this plate is full of negative charges. And the negative charges don't want to be kind of all stuck next to each other, and so it tries to escape by the electrons flowing around this way, should be anti-clockwise. Yeah, anti-clockwise. And then at some point, basically a little bit of current starts to flow. Okay. And you can see that the amount of charge here is actually going down. Okay, see at that point. So if I got it exactly the right point, there would be no charge actually on the capacitor. And then, but at this point, there's actually some current that's flowing through here, right? And then what the inductor wants to do is to, if it has some current flowing through it, it wants to keep that current going. So what the inductor does is to say, okay, well, I've got, we can see how many amps is flowing through here, 6.78 amps. So the inductor has 6.78 amps flowing through it. Now it wants to maintain that 6.78 amps, right? So it will actually actively try to keep that current flowing, but actually the capacitor doesn't like that, and we can see that because charge will start to build up here. Okay, so more and more charge is going on here, and then the capacitor is like a battery, can sort of recharge a little bit, but then at some point there's a limit because there's so many electrons here, and all the electrons don't want to be next to each other. So now the current is all the way down, but then the voltage across the capacitors will be now pretty big, like it's going up to 30 volts. And then now there's a lot of electrons here, and then the capacitor will want to discharge. Now you can see that the current is now going the other way. The voltage is now going down, the current is going up, until it goes, keeps on going around in a cycle like that. Okay, so that's basically the microscopics of what's actually happening in this tank circuit or LC circuit, whatever you like to call it. And let me go back to the slides now. Right, so this figure just explains what I was just saying. I talked it through on the animation because it's a little bit easier to see, but basically it sort of goes between a lot of electric field or voltage between on the capacitor to a lot of current through the inductor where there's a lot of magnetic field, and then it sort of just cycles through both. Okay. So this is our sort of second version of making a radio. So instead of just directly connecting the wire to the signal that we want to send, we actually now connect it to this tank circuit or LC circuit. And basically what this does is just like what the guitar does. If you imagine like what a guitar does without without this body, you wouldn't be able to hear the guitar very well. So the effect of the LC circuit is to add this oscillator to the sound, and then this greatly amplifies the sound that's coming out. So all of a sudden, when you connect this amplifier or this tank circuit to it, the signal that's coming out of here is much larger, and so you can have much, okay, it's lights. It's basically light, so you can't see it, but much brighter radio waves coming out. Now, actually, it's the reverse is also true. So when you have a receiver, you also it's better to have one of these LC circuits or tank circuits, because basically, if you've got the oscillator, next to your, say if it was sound waves, if you have some way to oscillate the sound waves, then you'll hear the sound much better. And so you have another LC circuit actually in your receiver, and this will pick up the radio waves much better. So, this is one of the demos I prepared. It's not, I think we're not missing out too much on this particular demo, but if you've ever seen the inside of a radio, it looks a little bit like this. And I just bought this on Taobao. It's just a little radio kit. It tells you how to put together the circuit and, wire your resistors and transistors like this. It's a very simple circuit, and put a battery inside here. This thing is the tuner of the radio. Okay, so what this actually is a variable capacitor. So in this circuit, it's actually, I think it's this element here. Actually, I'm not quite sure what this element is, but I think, well, one of these is a variable capacitor. It should be this one. And this one is the inductor. And this is really the main, important part of the whole, radio, because basically it's this combination of this inductor, and this thing here is the inductor, right? So that you've got this kind of iron coil with a, some fine wire going around it. And this basically forms a inductor, and this forms your variable capacitor. And just by changing the capacitance of this capacitor here, which on this circuit here, then you have different kind of resonances of the LC circuit, and it will oscillate at different frequencies. And this is what allows you to pick up on particular frequencies that are being transmitted by the radio station. So, when you're tuning the radio, then, you're actually changing the variable capacitor here and changing the resonance frequency of your LC circuit. And by basically changing the capacitance, so it's the resonant frequency is of the same frequency as the radio station, this is the one that it will pick up. Now, the rest of the circuit is basically just, converting that signal, boosting that signal so it's a little bit louder in your ear. In fact, I think I've seen radios, circuits for radios that actually don't use any electricity at all, which actually sounds amazing. I think as a teenager or a kid, I used to, play with some electronics, and you can wire up some circuits, and you can pick up radio stations, and it's very faint, like you can't hear it very well, but you can actually hear the radio even without any batteries at all. It's just that if you want it a little bit louder, like proper volume, so you can actually enjoy it, then you need a amplification circuit. And so this is basically what all this stuff is, just to take that relatively small signal, electrical signal, boost it up to something that's a little bit more listenable. That's why you need a battery. If you're happy with the very, very low volume, then you don't actually even need a battery. Okay, so so obviously we can't do the demo, but anyway, the main point is just so that you've probably seen these things in circuits before, but never really appreciated what that is, and that thing here is. It's basically all about the LC circuit. Okay, another point is often, with these old type radios, you're out there and it's like trying to, orient the radio and antenna in some way so you can hear the radio station, right? So I guess that's also part of this demo. So when I tried this at home, basically you got to point this thing kind of in the right orientation to pick up the station, right? Like you got to, if you're pointing it like at some angle, that's the wrong angle, you can't hear the station very well at all. And so, you're there sort of trying to orient your radio to hear everything the best you can. And basically the reason for that is that, radio waves are usually sent out with a particular polarization. And the polarization means basically which direction this electric and magnetic fields are pointing. So it's usually such that the radio waves are sent out with vertical polarization. I guess mainly because the antenna is something that's super high, and that's basically going up, right? You want it high because you want to broadcast it, obviously, and the the polarization ends up being in this vertical direction. And so when you want to pick up the radio signal, then you need to orient your antenna in the same direction. Okay. Yeah, and this is just talking a bit about frequencies that are used for communication. So we're gradually getting on to how mobile phones work, but basically mobile phones work in the same kind of way. So if you have there's various frequencies which are dedicated for various uses. Okay, so what we've been mainly talking about are sort of radio waves, and this is this kind of range. So AM radio, well, shortwave radio, okay, FM radio, and this is analog TV, I guess. This uses frequencies that are basically in this kind of range. So you might be surprised to hear that the wavelength of AM radio is actually huge. It's like hundreds of meters actually. So the wavelength, if you could see it, it would be like a building, right? Now, for FM radio, the wavelengths are much smaller, but still sort of in this range, around about the 1 meter. And then mobile phones and these types of things, the wavelengths are even smaller than that, somewhere between 1 and 10 centimeters. Wi-Fi is even shorter wavelengths, and yeah, and so forth. So all this stuff is fitting into this region of the electromagnetic spectrum. So all this stuff is stuff that you obviously cannot see. It's longer wavelengths than our eye can actually detect. Above that, high frequencies are like infrared. So that's sort of heat and things like this coming off in the infrared frequencies, and then there's a visible light range and so forth. Okay. So right, yeah. So this kind of explains a little bit how why transmitters look the way they are. So so things like, as I said, AM radio transmitters, wavelengths can be something like 100 meters, right? So this means your antenna also has to be, well, the transmitting antenna should be also something like that in order to best optimize the sending the radio signals, right? So that's why AM radio towers are usually giant, giant things like this, horses here for scale. And the good thing about AM radio and even shortwave radio. So shortwave radios, okay, so that's slightly shorter wavelengths, but still pretty long. Is that their range that they can transmit is actually very, very long. So an AM radio station can actually bounce off this so-called ionosphere. So this is some part of the atmosphere. And because it can bounce off, it can actually travel even longer than like kind of the horizon. So, normally, light does not travel longer than the horizon. Of course, see the sunset, sun goes down, basically it becomes more or less dark straight away. But radio waves are a bit different. I mean, it can sort of bounce off things and travel for very long distances. And so this is why, I have have friends who are kind of into shortwave radio, and you could listen to radio stations from different countries. Some point, my family, we were living in Indonesia, and I remember my father had a shortwave radio, and we were listening to just the radio from Australia, because that was days before the internet. This was the only way that you can get like direct live news and things like that from other countries directly, right? Otherwise it would have to be through newspapers, and that would be like, could be a day old or something like that. So yeah, so that's AM radio. FM radio, the wavelengths are a little bit shorter, and wavelengths about one meter or so. Maximum range is more like 100 kilometers. These do not bounce off the ionosphere, as you can see here. So they're not suitable for this very long distance broadcast. And then finally, mobile phone towers are much more compact, and basically because the wavelengths are also much shorter. So the wavelengths that we're using, say for 5G, are somewhere in the 1 centimeter range. And these ones, the ranges are much shorter. And so this is why you can't just have like one giant mobile phone tower somewhere that serves the whole city. This is what they used to do, things like TV and radio. You just build one giant tower, and then that covers the whole city. But for mobile phones, because the ranges are so much shorter, you need to build many of these towers all over the place. And well, that's partly a function of the wavelengths that are being used, but we'll also see why we can transmit so much data using mobile phones. Okay, so I think maybe we'll leave it there today. Yeah, so definitely for next lecture, please make sure you prepare in advance to do your presentations. So we'll try and get through, maybe at least, well, probably 3 groups might be the maximum for the next lecture. So please, groups number, I guess, 1, 3, and 4, definitely make sure you are ready to present on Wednesday. And so I'll look forward to hearing them. And any questions for anything today? Nope. Okay. If not, then I will see you on Wednesday then. See you then.
See you.
Bye.